Just kind of run you through the plan for today. As the title suggests, we're going to talk about a quick introduction for 3D design and prototyping. I am expecting that everyone in the call has got some level of knowledge, and what I'm going to talk you through is the basic idea of how we introduce this to freshmen. So we know when the freshmen come into our programs, some of them may have had exposure to CAD and additive manufacturing, rapid prototyping, CNC machining. They may have had that in high school or for hobbies, but for the most part, they don't. So I'm going to walk you through a set of slides that I normally use for my students, and I'll give you an alternate as well. The two you could also use for your freshmen. So the whole thing is geared to students that have no experience. It's possible for students that have experience to work ahead by themselves and try things that are more advanced. Normally I spend about 2 hours doing the introductions and then have students go out and 3D print a part by themselves. So we'll kind of move through it quickly, but what I'll show you is what you would do with a class and obviously the time you take for questions and other interactions. Feel free to ask questions during the presentation as well. Okay, so I usually start off with a basic idea of what rapid prototyping or 3D printing is. Most of the students know the word 3D printing. Rapid prototyping is a little bit of old school. Later on, once I introduce topics of machining, then I bring out the name additive manufacturing. But again, usually 3D printing is the best way to start. So I lay out that they're going to do some CAD work. They're going to create a model, and then they're going to take the model over to a 3D printer, print the thing, and then after post-process if necessary. To give them a basic introduction, the pictures at the bottom help make them aware that the format is triangulated. What they get out of the machines is not going to be smooth or perfect. So the next step is usually having them download a free CAD package and then walking them through the basic design and production process. In fact, I'll walk you through that pretty quickly here. The package that I use normally is called SketchUp. And let me just pull that up. Okay, so as an engineering package, I will not lie, SketchUp is not a great CAD package, but the learning curve for it is extremely flat. They can learn and develop parts fairly quickly. It is well suited to architecture, but it's perfect for an introduction. If eventually they're going on to learn something like SolidWorks or Creo Pro-E or some other package, this also primes them nicely for the concepts. I'm going to, let's see. Let me just show you where you get SketchUp from. Okay, so no, maybe not. SketchUp can be downloaded. Again, it's free. There's two versions. There's a Pro and a Make version. Just have the students download the simplest one. It comes down quickly. It runs on Mac or Windows, so you can accommodate all students. The process, there's a little bit of registration, but nothing that complicated. So the download usually takes about 5-10 minutes, depending upon the speed of the network. While it's coming down, you can talk them through or start giving them an introduction to the software. I'm going to move back over to SketchUp. So with SketchUp, there's a few templates. It's actually very well suited to architectural work, but for what we're going to do, 3D printing in millimeters or inches, if you want to, is fine. So pick the 3D printing millimeters option. Can everyone see that?
Yeah.
Okay. So what you should see is something that says MakerBot Replicator 2X. MakerBot is an older 3D printer. It's actually a very nice model. This one comes up with that workspace for the printer. I usually just leave it there for a little bit so students can get a sense for what they're looking at. With SketchUp, it's fairly fast, standard types of CAD tools, but you can have them click and create a rectangle. Just draw the rectangle quickly and then do a simple extrusion. It is, as you can see, it's very fast to make simple shapes. It definitely is not a parametric modeler. So to go back and make modifications, you basically have to go back and recreate again. If you want, you can also do features like holes. Now, an interesting thing, if you notice the bottom of that is flashing, a lot of us recognize that it's just the overlapping planes for the CAD model. But the students are very used to seeing that from playing computer games. You get these glitches from time to time, so they'll know what it is, they'll recognize it. But at this point, if we delete that template box, we can now see that we've got a full solid with a hole inside. So I think you can see fairly easy and fast to create. Simple primitives, simple geometries can be put together very quickly. So for free-form design, it's really not an issue. Now, SketchUp is not a solid modeler, it's a surface modeler. So you can do things that nobody should ever do, like that. So if you delete a face, you have a geometrically impossible shape. Basically, you've just got a skin. So with that, there's a few ways you can solve it. SketchUp will just let you redraw a side and it will infer there's a face there. Other options you have are tools like Solid Inspector. Now, this is one I have the students download. I'll show you where to get that in a minute. When you run Solid Inspector, it tries to identify problems. You can see how the boundaries, the borders turned red. So it's told you there's a problem there. So sometimes you get lucky and it fixes it, and this time we don't. So I'm just going to back up one step. And run Solid Inspector again. And it says that we have a good solid that we can produce. If you've done a lot of 3D modeling and additive manufacturing, you'll know that sometimes you get models with tiny holes in them or big holes. They create problems when you go to print. So this is an easy, fast way to check. Let me Okay, so SketchUp, as you start, is a pretty bare bones piece of software. They've got something called the extension warehouse where you can get additional functionality, and most of it's free. I'm just going to, okay, so this is the extension warehouse. You look, there's a number of tools. The one that we want is that solid inspector. So it's not a very complicated tool. It basically goes through and checks to just make sure you've got a complete volume. The surfaces in SketchUp are all flat polygons, rounded to look more complex. So this is the Solid Inspector plugin. You can see there's a little video that goes with it. There's description as well. Now I have these students install this one, and they also need to install a tool to export to STL. And STL is going to be our format of choice. Some students, usually it'll take about 5 to 10 minutes for students to get those downloaded and installed. Some will do it very quickly and some will have problems. So the ones that do it quickly, I usually suggest they just go out and look around a little bit. So here's an example where there's a plugin that does 3D doors, windows, and frames. So you can download it. It's great if you're doing architecture work. And so once they have the two plugins installed, they go back to SketchUp. Again, they check to make sure their model is good. And if it is good, then we export it to STL. Now, if you're very familiar with additive manufacturing, you'll know there's a few formats out there. STL is the oldest, but it's also the most universal. There's some other formats like OBJ, very good also, but not quite as universally supported. So I usually just tell the students to save everything to STL, and it cuts down file compatibility problems.
I have a question.
Yes.
Is this model you just made is a hollow or solid?
All right, so that is not an easy question. But let me, are you familiar with the insides of the tools?
No.
How about this? I'll do 2 levels of description. What you see is a winged edge model with flat polygons. So the outer volume is defined, but the inside is not defined as a volume. So it doesn't strictly enforce that every model must be a solid. So hence I'm calling it a surface modeler. Let me give you an example of what that means. So you may be able to see here, I've zoomed in. You can see that our round feature actually has flat facets. And this hole is probably made up of 24 flat polygons. All right, so now I'll do something nobody should ever do. By erasing the line, I've made the hole go away, which, you know, in a solid modeler, you could not do. Let me bring that back. I can also delete the inside. And I've got basically an outer box, just a skin with a hole on either side. Again, it's an impossible shape. Does that answer your question well?
Yeah, I think it's a hollow, right, inside.
Right. Think of it as a balloon, right? All you have are the walls, and if you cut a hole, which we've got here, it's a hole in the balloon. We cannot make this part on a 3D printer. So we would have to fix that. In a solid modeler, it would not have let us do that. Okay, so I'm going to export this in STL. So there's a few choices. Millimeters is a good set of units, but you can use inches as well. I usually save the file format as ASCII, and I'll show you a little bit, but ASCII is plain text. And then just for simple purposes, I keep whatever the default file name is. I'm just going to save that. And at that point, I'm actually done with SketchUp. So for education purposes, what I like to do is that STL file that I've just saved. Because I saved it in text format, I can open the file and show the contents to the students. And it emphasizes that the STL file format is just triangles. You can see, maybe a little tight here, but you can see that the whole thing is defined with triangles. It's got a direction defined, 3 points, and the sequence of the 3 points are used to do a cross product and determine which side is out. So it is possible to have a backwards face on a solid. So they've got the file. Then they open up a package called Cura. Different 3D printers have different packages. They all have essentially the same operation. So this Cura package is for, if you'll forgive, is for a Lulzbot 3D printer. Again, each of the 3D printers, they all have very similar software. For this one, I'm using a Lulzbot Mini. It's a pretty nice printer. It's about $1,200. I leave them up for the students, and they beat them up quite a bit, but they just keep working. So it's a good option. There are much lower cost ones, but they may take a bit more maintenance. There's also higher cost ones that have got some really nice features. The software, it's all free. In fact, there's alternate versions. So there's even Linux versions, Mac and Windows, so you're not stuck. But the one that I'm showing you is called Cura. And this software does two things. It will take the solid run. I'm going to go back to this. That checkerboard is the build plate in the 3D printer. So basically, if it fits in that plate, it'll build it. So students, the first time you do this, it's a little bit of magic to them. So in this case, I've just dragged the STL file from the side into the platen. I can actually drag multiple models in, and it'll take care of repositioning. So a couple of things to point out to the students before you go too much farther. In this software, the critical information's on the upper left-hand side. So you can see that it's a 2-hour, 20-minute build, and it uses 82 grams of material. So in effect, that's about $2 worth of plastic, so relatively inexpensive. So I've got the two pieces on the build platform. A 2-hour build, for an example, is excessive. So what I usually do is you pick one of the objects and you scale it down. So I'm just going to take that down to 0.2. In fact, I'm going to get rid of the other model here too. Okay, maybe that. All right, let me restart that one. Okay, so I've got the model there. I'll scale it down so it's a much more reasonable build time. So 0.1 gives me a 1-minute build, but that's much smaller than a centimeter. 0.2 gives me 6 minutes. 0.25 gives me 9. I usually shoot for about 10 minutes. It gives a reasonable build time, lets them see how the machine operates, and lets you move on to other things. So there's the build platform. We've got our part in the middle. This is also a good time to discuss how you deal with part orientation. This part needs no support material. You can lay it out so that you have a part that needs support material and explain to them that a part like this with the hole would have nothing to support the top material. And so the results, it may print, but the top of that hole is going to be rough. So you can explain to them how you add support material. There's a couple of simple, look to the left of this software, a couple of simple options to check. I'm just going to take this and put it back so it doesn't need support material. Roughly half the students will be a little careless with their first designs and build things that need support material. And after they've had to clean up the models, they appreciate why they don't want support material. So I'll run through the next things. The material type, the printer I've got with me on my desk has ABS, but there's other material options, including PLA, which is really a forgiving material. HIPS, also a good material, but there's other much more unusual materials as well. But PLA is kind of a good choice if you've got students going the first time. When they have choices, steer them to high speed, high detail, and see changes 9 minutes to 23. Standard goes from 9 to 13. And there's really no benefit in terms of the build quality unless they're really after fine features. So at this point, I've got the part ready to go. It's positioned in the platform, generally in the middle. Make the students aware that putting it close to the middle gives them better builds. And then with this one, I go up to File, Print. It opens up a little printing dialog. So I'll turn this on. I won't finish the build, but just to give you an idea. So I've just turned on my printer. You get a little bit of fan sound. And you'll see it connects to print. At this point, you can basically click and go hands off. So while I'm waiting for the printer to warm up and get ready to go, I usually return to the slideshow and then walk them through a bit more. So I showed you in SketchUp the model. I broke the model by deleting a face. So we let them see an example there. We talk about much more complex CAD systems. Here you see SolidWorks, and the model's got a couple of gaps in it. So you make them aware that that can be a problem. Talk about how the file format, you export it to STL, so the nice rounded things become these triangles, and you can adjust the resolution. And of course, that model gets broken up into triangles and then ends up in a file format like that. Explain to them the idea of slicing. So it brings that STL file in. It slices it into many small layers. And if you're familiar with it, the layers are all done as G-codes. So we've got the machine I'm printing on. That's what you can hear in the background. You can see a sample piece here. And of course, you can hear the machine running. In a class, the students would hear this. It's about to self-level. So I'm just going to turn this off for sanity. So you can continue talking while the machine's going. Talk to them a little bit about the material types. If you've got a makerspace, chances are you're going to leave out PLA. You can make them aware there's some really interesting materials. NinjaFlex is great. It's flexible. You get materials filled with woods or metals, graphite, so you can get conductive things. It's great. But the only material storage issues you've got is some of them, especially PLA and ABS, they're hygroscopic and they will absorb water. So if you've got a makerspace or you're warning the students, leaving the materials in the sun or in a moist place is not a good idea.
Do you suggest hatch box?
Sorry?
How about a hatch box? Do you think that's also a popular material?
Sorry, give me that again.
Hatch box. You mentioned a list of material, but I don't see a hatch box.
Yeah, this is a limited set.
Oh, okay.
Because again, they're beginners. You just give them enough to be aware there's lots of materials out there. With beginners, though, if they're going to carry their own rolls of material, giving them a couple of warnings will help them from getting brittle or degraded materials. So I mentioned the support materials before. This is a good chance to illustrate the concepts. So here there's a couple of pieces. You can see that there was no support material, but it's basically a bridge. There's nothing to hold it up. You can see the fuzzy or the poor quality underneath. And then you can show them the other half where there was support material. The object was printed, but then they've got to get off all that white component. So it kind of makes them aware of why they can use support material, but they don't want to. Now, if you get students where they're moving a little more towards the design aspects, you can emphasize the staircase effect in the designs. You can talk to them about accuracy. So high detail is usually 1/10 of a millimeter, and high speed, like we did there, is about 0.4 millimeters. All of the parts, they do tend to grow. So if you're familiar with it, the maximum material condition, it's always maximum material by about 0.2 millimeters, depending upon the printer. Small holes get smaller and pegs get bigger. And then the other problem is warping. So every student loves to build a big flat thing the first time. If you can warn them that the flat pieces tend to curl, You can save them a lot of grief and concern. So what I'll do here, now just to kind of move to discussion and questions, there's a few things to consider. Makerspaces, these days a lot of schools have got 3D printers and other equipment someplace. Some have got large dedicated maker spaces, and some it's just equipment tucked in a corner. But a lot of students also have personal access to 3D printers. With CAD software, I showed you SketchUp, which is easy to use quickly, but it's very limited. So other great options, Autodesk has Fusion 360. They also offer something called Tinkercad. Fusion is more advanced. Tinkercad is actually usable by elementary school students. FreeCAD is nice, and in fact, if you're going to do it, that's a great alternative to Fusion. With the students and what I do, I typically go through the tutorial and then give them a structured design tutorial. One example is something like a key tag. I'll show you a couple of examples once we wrap up here. The first assignment I like to do is something simple like a key tag, so something that's relatively flat and angular, rectangular with a hole in it, and some custom design. After they've done that and they've gone through the process with the tool chain, the next thing is to give them something that's open-ended, a lot more exploratory. And you'll find some students will go way beyond your expectations. Some will just meet them. But at the end of the day, students in all disciplines from electrical, mechanical, manufacturing, they all have a great time. They all turn out some really interesting solutions. Okay. If you have any questions or you need help, or if you want copies of this slideshow or another one I use, there's another one with a lot more slides. Feel free to send me an email. You can see my email address at the bottom there. And I love helping groups get this type of thing into the curriculum. So just let me know if you need any help whatsoever.